A very good morning, students. In today's class, I'll be talking about nucleophilic substitution reactions for halo compounds. Nucleophilic substitution reactions are of the type: you have a haloalkane, you combine it with a nucleophile. Nucleophile is a nucleus-loving identity. You very well know nucleus is a positively charged identity due to the presence of protons, which are positively charged, and neutrons, which are neutral. So since if something is going to attack a nucleus, means it should have a negative charge, or it can also have a lone pair of electrons. For such a reaction, since we very well know this bond has a single bond character because the carbon is sp3. This X leaves as an X minus and the nucleophile attacks, leading to R bonded to a nucleophile and the X negative is liberated. So you are substituting a nucleophile Nu minus with an X minus. Such a reaction comes under the category of nucleophilic substitution reactions. These reactions are generally written as an SN reactions, where under this category there are two more ways of classifying it. One is SN1, which I'll be taking up first, and the second is SN2. There's a significance of 1 and 2 which we'll deal with a little later. A nucleophilic substitution reaction, as you can see, requires removal of an X and attack of a nucleophile. There are actually two steps involved. One, to remove an X, and second, to attack a nucleophile. Now, the situation where both the steps takes place one after the other, that means it would be in two steps, is called as SN1. Whereas the one in which both the steps take place together, two together. So 2 stands for 2 together, 1 stands for 1 after the other. That is my way of making you understand. Otherwise, that's not how it is. It actually means a unimolecular, and this refers to a bimolecular. Where unimolecular means depends on only one molecule, where bimolecular means depends on both the molecules which are undergoing the reaction. But an easier way, as a keyword, you could remember SN1, 1 stands for 1 after the other. As soon as you remember 1 for 1 after the other, you quickly come to 2-3 conclusions. If it's 1 after the other, it has to be in 2 steps. That is clearly understandable. Now, to broadly classify these two as this, I'll take up one after the other. The first one I'm talking about is an SN1. In case of an SN1 reaction, what happens is you have a reaction where you have a tertiary alkyl halide. This is your tertiary alkyl halide. Knowing it very well that the tertiary alkyl halide would easily liberate the X. The X pulls away the electrons towards itself and goes off. If that happens, you are left with a carbon having 3 R groups and the X is lost as a negative charge. Of course, you will have a positive charge developed here. This situation where the bond is breaking is not easy. This is a slow step. That is why we put a reversible arrow. This becomes a slow step. A slow step is always rate determining step. Your speed of the reaction depends on this particular step. The product formed is a carbocation. The carbocation is sp2 because it has got only 3 bonds. Also, it has a planar geometry. Second step involves the attack of the nucleophile, in which case you would have the carbocation with the 3 R groups, and the nucleophile has to attack. Now your nucleophile can attack from both the ends. It could be one by one side and the other way could be from the opposite side. Since there are 2 possible ways of attacking, it's quite clear that you would end up in 2 products. Let me take this as the route A and this as a route B. So a route A if is followed, then I would end up in nucleophile on this side, carbon with 3 R groups. While if route B is followed, then in that case the nucleophile is attacking from this side and you have got the 3 R groups like this, which means your two products are similar with respect to the bonds around the carbon, but their orientation in space is different. You have nucleophile from this end, in this case you have a nucleophile from this end. These two are stereochemically different products. They are different with respect to their arrangement in space. So you have got two different products. Also, you have got a planar carbocation formation, which is your rate determining step. So this becomes the first order reaction because your reaction is dependent only on one of the reactant. The second step is a fast step because it involves the attack of positive and negative identities. The slow step is the rate determining step. Hence, you end up in a reaction which follows first order kinetics. This one is your unimolecular, which means the reaction is dependent on only one of the reactants, not both the reactants. It is also called as a first order reaction. We prefer a protic solvent is preferred. Protic or polar solvent would be preferred. Why so? If you have a polar solvent, the solvent would have a positive end to it and a negative end to it. It would have a dipole moment. Hence, it would stabilize the two products of the first step. Hence, making the first step faster. So, the polar solvent prefers the reaction prefers to move into SN1 mechanism in case you have a polar solvent. So I'll just give a quick recap. SN reactions are for nucleophilic substitution reactions where it is classified as an SN1 and SN2. Presently I am doing in detail the SN1 mechanism. SN1, the key word that I would advise you to learn for an SN1 is one after the other. If it happens one after the other, then it is quite clear it will take place in two steps. The first step is the slow step, hence your rate determining step, where you have a carbocation formed, which is sp2 and planar. The second step involves the attack of a nucleophile, which could be from both the sides, leading to formation of two products which are similar with respect to melting point, because their bonds are same, boiling point, because their bonds are same. All physical and chemical properties for these two products will also be same. But where is the difference? The difference is in the arrangement of nucleophile in space. The orientation in space of the two product formed is different. This particular product is opposite to the one that you started off. Your X left from this side while the nucleophile is attacking from the opposite side. So this particular product is called as the inverted product. While this particular product, you have nucleophile attacking from this end, from where the halogen left. So your halide left from this side and the nucleophile attacked from this very end. So this product is also called as the retented products. So the two products that you form are, one is inverted, opposite in geometry, opposite in arrangement in space, and the second is called as the retented product when we talk about SN1 mechanism. My next lecture would be on SN2 in detail. I close my lecture here today. Good luck.